Thank you all for joining us. We're the Automated Guided Vehicle Capstone team. Our team includes Devin Ayotte, Damian Badical, Jackson Koch, and myself, Robin Reid. Our client is Chris Dick, our technical advisor is Dan Barrett, and our communications instructor is Joan Magnuson. This presentation will be roughly 10 minutes long with a question and answer period at the end. In this presentation, we'll cover our problem statement, the scope of our project, and some constraints the team faced during the duration of this project. We will go through the functional analysis chart, which will walk us through the process of this project and the individual steps that are taken in completing our goal. We will finish this presentation with a conclusion and any recommendations our team is making. Next slide, please. SAIT has replaced a fleet of 4 Festo Robotinos that they have not had the opportunity to finish configuring for the desired tasks. The remaining configurations are to be completed and set up to automatically deliver trays to and from robotic work cells in the mechatronics lab. You can see to the bottom right corner. This will be carried out by safely avoiding static and dynamic obstacles while maintaining the current functionality developed by previous group projects and courses. Next slide, please. The scope of this project involved the development of an autonomous guided vehicle that is based to work on a Robotino platform. It is commissioned for use as a method of transfer of materials between work cells in the SAIT Mechatronics lab. An example of the work cells are to your left, or to your right there, sorry. Proper wiring has been completed on the Robotino based off the professional practice judgment guidelines used in mechatronic skills competitions, and electrical documentation has been provided. A gripper conveyor system has been designed to transfer parts. The Robotino is programmed to autonomously function in the lab while students and instructors are present. Safety of instructors and students is a top priority. Autonomous battery tending is included in the functionality of the Robotino's programming, and this project will contribute to the vision of a fully autonomous lab. Next slide, please. Safety is a primary concern in this design, as the Robotino is sharing a space with people as well as expensive and occasionally automated equipment. The design must be able to recognize obstacles and respond to them in such a way as to prevent collision. Installing a gripper for the purposes of this project must not interfere with the current factory gripper configuration that is used in other applications. And additionally, the team has faced challenges due to COVID-19 limiting the access to resources such as lab time. To the right, you can see a picture of our input-output interface, as well as a cost map of the lab we're working in. Next slide, please. This is an example of our functional analysis chart, and in the top left corner, you can see a highlighted square that discusses requesting parts through the ABB robot interface. Next slide, please. Our project uses user input and socket communication to determine pickup and drop-off locations, using socket communication to communicate between an information hub and the ABB robots. As you can see to the diagram, at the diagram on the right there, we have our our ABB robots and then our information hub or information node. The information hub will hold the status of the ABBs and confirm whether a call for transport is able to be placed. The team has programmed 2 executable procedures that are able to be added to any routine programmed on the ABB robots. These procedures will allow the user to request part movement from the Robotino. The user input will be sent to the information node where the status of each ABB is monitored. And if the ABBs are safely able to send and receive materials, the request will then be forwarded to the Robotino containing any necessary information such as coordinates for the pickup and drop-off. Next, we will go to Devin, who will discuss our program logic.
All right, so as we can see in the functional analysis here, once the pickup is requested, the first thing the Robotino does is check for sufficient battery charge. And it is able to do this because the battery information is constantly being provided to ROS in the event that it should be called. Before the call is actually placed, there's a great deal going on at once in the background, and that brings us to the strengths of ROS and why we chose it. It greatly simplifies simultaneous operations, as just programming this in Python or any other sort of linear programming language would be extremely difficult. So a strength of ROS is that all of these simultaneous operations are very simple to implement, as all of the communication in ROS is structured according to the ROS computational graph. You can see a few elements of it in the diagram at the bottom right here. It structures all of this inter-process communication in black boxes called nodes. So it's very easy to collaborate using ROS. You write your portion of it with a defined input and output, and this part can be used, reused, edited, and most importantly, developed independently of the rest of the program. You establish what's going in, what's going out, and you don't need to coordinate as much with other groups or other members of the group as you're developing this. This makes collaboration simple, but it does come at the expense of some fairly elegant solutions to very simple problems. And we'll get into this in our conclusion and recommendations. We found that often the solutions that we were using provided by ROS were a lot more complicated than the problems, as there are many different elements, sources of information, inputs, outputs going into this program. And I will now pass it off to Damien to discuss the navigation.
Thanks, Evan. Next step is to travel between the ABB cells. And in order to do that, we make use of 9 existing infrared sensors at the base of the Robotino, as you can see in the next slide, bottom right picture, to sense close objects. In addition, we added a Kinect structure light depth camera for 3D imaging and long-range obstacle detection. On the next slide, you see we use the camera to localize the Robotino. We use the odometry data from the wheel encoders to counter for drifting of the Robotino, because the odometry data is not exact. We additionally use an algorithm named real-time appearance-based mapping, where a feature extraction algorithm loops over frames, 3 frames per second, and tries to match the current frame to a previous one. This method is called loop closure. If a loop closure is detected, the odometry data is adjusted and the map is fitted accordingly. On the next slide, you'll see a complete 2D graph of our mechatronics lab, where the black area indicates obstacles and objects, the light gray area free zone, the dark gray area unknown environment. The blue lines indicate the path we took while mapping, and the yellow lines in between indicate loop closure exceptions, and the red ones loop closure rejections. Using this, we were able to create a 3D map of the lab that you can see on the next slide. And now we're coming into the actual navigation part on the next slide. For the actual navigation, a path is planned to avoid any contact with an obstacle. The picture shows the inflated obstacles. So you can see the dark area is the actual obstacle, and then we have a safety zone around it, the blue area, as well as we have cost maps overlaid that indicate how difficult it is to pass through a certain area. The planner will avoid to enter the occupied or inflated area with the footprint, and you'll see the whole thing functioning at the end in a quick video. I'll pass it off to Jackson with the gripper.
And now we're going to talk about the gripper and how the Robotino collects apart. Next slide, please. On our left, you can see a gripper model made in SolidWorks. How it works is there's a lead screw in the middle. The carriage goes up and down because the lead screw is attached to a motor at the bottom, connected to the lower mount. In the right image, you can see 4 limit switches and the springs, which control the opening and closing of the fingers. And you can see the fingers in the left image, it's all labeled. Yeah, next slide, please. Now we'll watch a video of it all working. So here we call all of our routines. Now you can call the Robotino from the work cell using the teach pendant. See, it's autonomously navigating to the work cell. Here it's really interesting because the robot is aligning itself using open computer vision, and 3 dots pretty much puts the center dot in the center, does a 180-degree turn, and now we got the gripper logic. See, so the carriage goes all the way to the top, it hits the limit switch, comes down for a certain amount of time. After that, it starts proceeding forward towards the conveyor. And at this point, the finger extensions will start to open. See, and at the back of the finger extensions, there is a limit switch. So that signals the carriage start moving down. Once the carriage has hit the conveyor, it will start backing out with the part secured. Beautiful. Next slide, let's get to our conclusion recommendations. All right, yeah, so in conclusion, yeah, our programming environment is a big part of it, and ROS was selected because it's flexible, scalable, and versatile. It can meet any of our clients' needs. It can do almost anything. We'll say that. It's great to learn as a student and a teacher. It gives you relevant coding skills, C++, or Python, and knowing something about it as a future M&T student can benefit you greatly. And this is why we recommend the continued use of ROS for future projects using the Robottino. However, it's complicated, so we recommend narrowing the scope of future projects so that students will have the time and resources to correctly document what they've learned, and then build on each preceding project can build off of it. And our last recommendations have to do with the gripper, and another iteration of the gripper is needed because in this last week, there's a small design flaw. The guide rods do not have set screws attached to them. So one of them fell out and broke off a small piece of the Robottino casing. So we recommend adding those set screws. It's a good idea for future capstone project. And our last recommendation is to add a forklift style attachment. Question and answer. Damien Batico will be moderating the question and answer.
Perfect. Thank you, Jackson. We are now ready to take any questions you might have.
Hey, Damien, Chris here.
Hey.
So you're the first project team for me that's used ROS. You had some concerns about its complexity. Can you just explain a little bit more about the difficulties you had using ROS for this project?
That is an excellent question, and we faced a lot of difficulties along the way. I'll pass the question off to Devin because he was mainly working with it.
So the ROS graph has specifically prescribed channels and methods of communicating. There are actions which are asynchronous. So you request a function from another node, ask it to do something while the main program continues to operate, or you can call a service, which is synchronous, and the main program stops until you get a result from that. And both of these things are difficult to implement. You've got to create additional message types and put in a bit of work to establish these lines of communication, whereas you can do the same thing with 2 or 3 lines of Python code. If you do that, you end up with kind of a messy mixture of metaphors, I guess. You end up with something that is difficult to understand for anyone looking at it, because you're using ROS, all of a sudden you've flipped over to a Python script or something. So solving some very simple problems, we had to start at the beginning creating these methods of communication, which was very tempting along the way.
And if I might add, one of the biggest challenges was the computational requirement, especially because we used a lot of OpenCV and optical recognition. Therefore, we used a client machine to control the Robottino externally, and we had issues to synchronize the time in between the 2 machines, which resulted in rejections of sensor data and commands because they were not perfectly in sync. We figured out the solution yesterday very late, but we were not able to implement it to like perfectly functioning.
Excellent, thank you. Anyone else have any more questions for these guys?
Hi, Chris. It's Greg James from Festo.
Hey,
How are
Greg, go ahead, please.
you? Well done, team. It seems like it was a successful project. Good to see you using the Robottino. I really liked the design of the gripper. I didn't happen to notice if you had a part presence sensor on the gripper assembly, or are you just solely relying on it picking the part? And is that something that you considered integrating in the future?
Thanks for this question. I'll pass this on to Jackson.
Yeah, so we solely relied on the part, it dragging the part off. We didn't have a part present sensor, so it's a very, very good suggestion to have a part present sensor for future groups. And yeah, that's a good idea.
That said, it seemed to work really well, and certainly we're looking at integrating a similar concept into our product line. So I was really pleased to see the outcome of your project. Well done. Thank you.
Perfect. Thank you so much. And thanks, Lane, for the comment.
Excellent. Thank you very much, team. We do need to move on. I know people may have more questions and comments. If you would like to, you can send them to me later and I can forward them to that team.